Hello and welcome back. In section 6.3, this is going to be about biased and unbiased estimators and normal distributions. So I think it's important to start out with an example to sort of demonstrate exactly what we're going to be talking about. So I think in the 2010 census, 74% of residents in Hill County here, including Havre, were born in Montana. So 26% of residents were born outside of the state. So if we were to go around and ask 100 people in Hill County where they were from, you would expect about 74 people out of the 100 to have been born in Montana. This is because 74 is the actual percentage. So if you were to survey 100 people, you'd expect about the same percent. But it's not unlikely that we get a number that's only close to 74. So maybe we actually get 75 people out of the 100, or maybe we get closer to 73. It could be as many as 80. Maybe we get 80 people say that they were born in Hill County. So the point of this, though, is that if we do this again and again and again, if I go out on a Monday and ask 100 people, if I go out on Tuesday and ask 100 people, and I continue doing this day by day by day, I'll find that most of the surveys are pretty close to 74. As in, I'll get 74% of people in my little surveys of 100 people. I'll get most of them will be around 74. But if I come up to 80, well, there will be fewer people born. I will conduct fewer surveys that say 80% of people will be born in Montana. Likewise, if I come down to 70, I could get 70% of people on my survey to say that they were born in Montana, but it seems a little bit less likely. And what you'll notice is that this is going to form a normal distribution. So as I conduct multiple surveys, the proportion of people in my surveys that were born in Montana will form a normal distribution. Most of them will say 74, like the actual proportion of people. A few of them, if I just get unlucky, a few of them might be a lot bigger than 74 or a lot smaller than 74. But those won't happen very often. So most of the data will be clustered around the mean, with a few data points going off, being a little bit further away from the mean. So to sort of summarize, as you look at each of our samples, and we look at all of the proportions in each one of those samples, they're normally distributed. Most samples will be close to the actual mean. With a few of our samples, when we get unlucky, we'll be a little bit further away. And when you look at the mean of all of the sample proportions, so again, when you look at the expected value of all the sample proportions, it's the same as the population proportion. So if I didn't know what the actual population proportion is, and I saw this graph, and I saw that, oh, all of the samples seem to be normally distributed with the mean of 74, that would indicate that that the whole population proportion should be 74. So this section is basically just discussing this property. So let's give this a little bit more formality. So the sampling distribution, okay, so just a couple of words. A distribution is describing a bunch of data values, and the sampling distribution is describing the data values from our samples. So the sampling distribution of a statistic, for instance, of a proportion, is the distribution of all possible sample statistics from samples of the same size. So we go out and we ask 100 people. One day we go out and ask 100 people. The next day we go out and ask 100 people. The following day we always ask the same size. We always get the same size sample. And we're always looking at the same thing. For instance, in this case, it's just the proportion of people born in born in Montana. And we have some different letters for this. So we use P for the proportion in the entire population, and P hat, so red P hat, is going to be the proportion in our sample. And as we do this again and again and again, the sample proportions are going to be normally distributed. Most of the time, they'll be close to the actual proportion in the population. Some of the time, they'll be a little bit further away. This is a normal distribution. And the mean of the sample proportions is the same as the population proportion. And there's a nice way of saying this, and this is using the word target. So sample proportions target the population proportion, meaning if you take enough sample proportions and you look at the average, the mean of all of the sample proportions, you should get pretty close to the actual one. Not only can we do this for proportions, but we can do this for other things. For instance, the mean. So we had mu to be the population mean, and x bar to indicate the sample mean. Again, if we were going to go out and look at maybe the average age of people, so we go out and ask 100 people, what is your age? And then we take an average of our sample. And we do this on Monday, and then on Tuesday, and on Thursday, and if we keep doing this again and again and again, our sample means will be normally distributed. And I've written tend here in quotation marks. There are some caveats here. The samples that we take have to be big enough, essentially. So if our samples are big enough, the sample means will be normally distributed, and the sample means will target the population mean. So if I go out and I collect enough samples, and I look at all their means, and I graph them, we're going to get a normal distribution. This is part one. And then part two says that the mean of all the sample means should be about equal to the actual population mean. So you can use all of our sample means to estimate the population mean. And then the last statistic that I'll mention here is the variance. Remember, the variance is the standard deviation squared, and we have sigma to represent the population standard deviation. So sigma squared is the population variance, and s squared is going to be the sample variance, s being the sample standard deviation. Sample variances are not quite normally distributed, but they're skewed right. So if I were to draw a graph of this, it's not going to be very symmetrical. It's going to have a long tail that goes to the right. However, sample variances target the population variance. So if you were to look at the average variance as in the mean of all of the sample variances, you should get about the same thing as the population variance. As in, the sample variances are a good estimator of the population variance. And then to sort of summarize, so a statistic used to estimate a parameter, as in something from a sample that you're using to estimate something from the population, is called an estimator. It's not a very inventive word. But the statistics that target the parameter, as in they're a good estimator, these are called unbiased. And the unbiased estimators that we've looked at are proportions, means, and variances. So if you want to know the mean of an entire population, we can go out and we can collect samples, and our sample mean should be a pretty good estimator for the population mean. We can do the same thing for proportions and for variances. However, medians don't work the same. If I want to know the median, say, age in Hill County, and I go out and I collect a sample, the median of the sample is not a very good estimator for the median of the entire county. Likewise, the range of ages in a sample is not going to be a very good estimator of the range of ages in an entire population. Standard deviation is the one that's so technically it is biased. However, if you use huge samples, if you use really, really large samples, the amount of bias is very small. So even if it is biased, it's still okay. It's pretty close to being unbiased. So standard deviation, while technically it's not a good estimator for some reasons, taking large enough samples will mean that it's still an okay estimator. And what I'll do in the next video is I'll go through just a couple of calculations that will show, say, the mean of some samples is going to be equal to the mean of the entire population, and I'll go through an example where I'll show that one of these estimators is in fact biased and is not a very good estimator.